operation is that of lube oil and hydraulic oil supply. Let's look at the lubricating oil system first. A continuous flow of lube oil must be circulated through all of the turbine and generator bearings. Typically, the arrangement would look like this for a single-cylinder machine. The lube oil supply header is maintained at about 50 psi, and from here the oil is force-fed through each of the bearings, including the turbine thrust bearing. After passing through the bearings, the oil flows into the return header, and from there to the lube oil tank. The lube oil is pumped from this tank in order to feed the supply header. So we have, in effect, a closed cycle. But there are some other important features. First, the need for cooling. As the lube oil passes through the bearings, it picks up heat and its temperature rises, conducting heat away from the bearings. The effect of this would be to continuously raise the temperature of the oil in the tank. In order to prevent this, a cooler is provided, and this is usually placed in the path of the lube oil supply. The lube oil cooler is usually of the tube and shell type, with cooling water passing through the inside of the tubes. It is normal to fit two coolers so that one may be taken out of service for cleaning at any time. Thus, the change can be accomplished without interrupting the supply of oil. Actually, the raising of lube oil temperature in the tank has a slight advantage in that it allows any moisture contained in the oil to vaporize. For this reason, a vapor extractor is fitted to the top of the tank to draw off any vapor and discharge it to atmosphere. But where does the moisture come from? Well, this may be picked up by the oil in its passage through the bearings with their proximity to the gland steam. The vapor extractor will also remove any traces of hydrogen that may infiltrate the lube oil from the generator cooling system. The subject of hydrogen cooling and its associated seal oil system is discussed in the power generation module of this program. More serious yet, the oil is likely to pick up fine pieces of metal and other contaminants in its route through the system. And these contaminants could cause serious damage to the bearings and therefore must be removed. Most lube oil systems include a filtering system within the circuit. This may consist of bag-type filters within the oil tank, or external cartridge filters, or a centrifuge which continuously circulates oil from and back to the tank. Maintaining the cleanliness and purity of the oil is extremely important to good turbine operation. Usually, the lube oil is sampled at regular intervals, say monthly or bi-monthly, and analyzed for impurities and other characteristics. The supply of lube oil is so vital to the operation of the turbine and generator that a standby pump must always be provided and maintained, ready for startup on automatic control. But one question comes to mind. What would happen in the case that we lost all auxiliary AC power? This could happen, for example, in the case of a turbine generator trip in a facility with no station service backup. We'd then be faced with the prospect of the turbine generator running down without the circulation of lube oil, a condition that could conceivably damage all of the bearings. In order to prevent this potential disaster, many machines are equipped with a DC oil pump, which would be fed from the station battery in such an emergency. Now let's move on to look at the hydraulic oil system. This system operates at a much higher pressure than the lube oil system, even as high as 2,000 psi in some machines.